In the last video we looked at a derivation of the Newton-Raphson method for finding the root of a function. We also looked at this example here. Here is a graph of the function. We saw that there is a root between 1 and 2. Actually, we broke down the interval further and we saw that the function changed sign over the interval from x equals 1.5 to x equals 2, which means there's actually a root between 1.5 and 2. So we know there's a root near 1.5. So we're going to use 1.5 as our first estimate for the Newton-Raphson method. Notice that our first estimate is referred to as x0, but of course we could call it x1, doesn't matter. So here's the formula for the Newton-Raphson method. So we plug x0 in to the right hand side and we get out x1, which is a better estimate. Okay, so we set n equal to 0 here on the right hand side. So that means we have x0 plugged in to the right hand side. So here our x0 is 1.5, so we're going to get 1.5 minus f of 1.5 divided by f prime of 1.5. So we need to get f of 1.5, so plug 1.5 into the function. That's straightforward. Next we need the derivative because we want f prime at 1.5. So first we need to differentiate this function. So the derivative of x is 1, the derivative of minus 2 is 0, the derivative of ln of x is 1 over x. We get f prime at 1.5, so we just plug in 1.5. So we get 1 plus 2 thirds, which is 5 thirds. So now we plug in, so into the right hand side we have x 0, which is 1.5, f minus f of x 0. So it's going to be minus 0.0945 on top, and underneath we have f prime of 1.5. So that's x0 gone in, and we get x1 out. Now we can use the Newton-Raphson method again. So here's x1. So if we go back to the formula, we let n equal 1. So we're plugging x1 into the right hand side, and we're going to get out x1 plus 1, or x2. So here's the situation with n equal to 1 in the formula. So we plug in x1, which is 1.5567. We have to get f of 1.5567, and we have to get the derivative of f at 1.5567. So there's f of x and there's f prime of x. We just plug in, solve that, and the 4 decimal places we get 1.5571. Now if we continue with this procedure and calculate x3 by plugging this in, we would actually also get 1.5571 to 4 decimal places. So that tells us that this is the root to 4 decimal places. Here's another example. F of x equals x minus tan of x. To use the Newton-Raphson method we have to take its derivative. The derivative of x is 1, the derivative of tan of x is sec squared of x. Now sec squared of x is the same as 1 over cos squared of x. And if you do some work here with trigonometric identities, you'll see that this is actually equal to minus tan squared of x. Okay, as a reminder, I'll just quickly go through this. 1 minus sec squared x is written down here. Get a common denominator of cos squared x. And cos squared x on top is the same as 1 minus sine squared x. Okay, cos squared x plus sine squared x equals 1. That's where this comes from. So cos squared x is equal to 1 minus sine squared x. So the ones cancel here, and we end up getting minus sine squared x over cos squared x. That's minus tan squared x. So our first approximation x0 is 4.5. So here's the Newton-Raphson formula. So we want to get f of 4.5 and f prime of 4.5. So here is f of 4.5. Plug 4.5 into the function, and we need f prime of 4.5. So we need minus tan squared of 4.5. And then we plug into the Newton-Raphson to get a better approximation, x1. Let's look at the function x cubed minus x plus 3. Now we see that there's a simple root between minus 2 and minus 1, because f of minus 2 is negative, whereas f of minus 1 is positive. So the function changes sign from x equals minus 2 to x equals minus 1. Now, from the previous video we know a simple root is a root for which the derivative is not 0. So you can see the tangent to the curve at this root is not horizontal. So we could use either -2 or -1 as our first estimate for the root. Both of those values are close to the root. And we can see that the curve is approximately a straight line for values of x close to the root. So the Newton-Raphson method should work fairly well. So we just go ahead and plug in. So we plug -2 in for x0 here. So we have to get f of x0. Well, there's f of x. Just plug -2 into that. Then the derivative is 3x squared minus 1. So we plug -2 in for x there to get the denominator of this formula. And there's a better approximation. Let's take a second iteration. Here's the Newton-Raphson formula when n is equal to 1 on the right hand side. And here x1 is -1.727. So now we plug that value in to get out a better approximation, x2. So we can do another iteration. So this is our third iteration. And notice that when we do a third iteration, we get 1.672. So the first two decimal places haven't changed for the third iteration. So we expect that for more iterations, the first two decimal places will remain 0.67. So we won't see any change there. So we know that our answer to two decimal places must be -1.67.